So here's a recap of what we've done. So what we've looked at is we looked at proportion for a while. So we have proportion, and we looked at this for a bit of a while. And we said that with proportions, we have the original proportion P. So that's going to be from the population. And we don't quite know what the population proportion is. So we are going to estimate it with P hat. Okay, so some of the things that we have done with the proportion is that we've tried to figure out what does the distribution of P hat look like, and the way that we've done it is with the central limit theorem. And what we said was that P hat is normally distributed with a mean of P and a standard error of square root of P, 1 minus P over N. So we've been doing this a lot. And remember that the required sample size, or it being large enough, depended on the number of successes and failures. So we needed NP to be greater than 10, and N times 1 minus P to be greater than 10, greater than or equal to 10. So that was one of the things that we did. We also did another thing, which was confidence intervals. So the CI, confidence intervals. And we also had a formula for that. We said that we can figure out what P is, or try to have a good estimate of what P is using the formula P hat plus or minus Z star square root of P hat 1 minus P hat over N. So that's what we said. It's really messy, sorry. And then we can try to figure out where P would be with certain amount of confidence. Afterwards, what we did with P hat was we tried to use hypothesis testing, HT, and we used the Z test to try to figure this out. This was trying to figure out what HO and HA was, and we tried to find the P value to either accept or reject this, the null hypothesis, right? So that's basically what we've done so far with P. So with proportion, we did a lot of 3 different things: central limit theorem, confidence intervals, and hypothesis testing. Okay, and now what we're going to do exactly the same thing, but now we're going to do it for the mean. So the mean, we know that the population parameter for the mean is mu, and since we don't really know what mu is in real life, we're going to try to estimate it with X bar. So what we want to try to figure out is, this is really difficult for me to figure out. I cannot possibly get every single person in the United States and try to figure out what is their average income, for example. So it's really hard. So instead, what we're going to do, we're going to get a sample, and our sample is going to be X bar, similar to what we did with P and P hat. And what we're going to do with X bar, we're going to try to figure out a central limit theorem, confidence intervals, and hypothesis testing. So we're going to do exactly the same 3 things. So first, we're going to start with central limit theorem. So let's start off with a very basic simulation of X bar. Okay, so let me just go here. So here what we have is a population of, maybe it could be GPAs, or it can be, I don't know, well, it's 16. It can be of something, I don't know. It's something, and we graphed every single possible observation, and we graphed it, and we got that. We have that the mean is 16, the median is 16, the standard deviation is 5. Don't worry about what skew and kurtosis means. Okay, so we have all of this. So what we're going to try to do, we are going to try to get 5 observations from this population. So this is what it's going to do. So let me animate it. So I'm going to get 5 different observations. So what I got is 5 different things from this population. I got these 5 things, I added them together and divided by 5, and I got a mean. So basically, I took the mean of these 5 things. This blue thing represents the mean of these 5 things. And what I'm going to be doing, I'm going to continuously be doing this over and over and over again. I'm going to get 5 more things, add them together, and get a new mean. Okay. So it's very similar to what we did with the proportions, that activity with the dice, but except that we're doing it now with the means. So if I continuously do this over and over and over and over again, well, eventually I will get some sort of graph for the means. So if I do this 10,000 times, what I'll get is actually a normal distribution. Okay, so I went ahead and did this over and over and over again, and the means of those and the sample means of those individual observations, the whole distribution of the means ended up being normal. Okay, so that's actually a really good thing because it can make us do a lot of other things. So now notice that the means are basically around the same, right? So if I were to get the means, whoops, what did I do? What does this do? Whoops. There we go. Okay. So notice that when I kept doing this over and over and over again, you can see that the means are actually the same. Here, the mean of the population is 16. Here, the mean of the population is around 15.99, which is around 16. So if I kept doing this over and over again, I will eventually get to 16. Notice that the standard deviations is different. Here, the standard deviation is 5. Standard deviation here is 2.24. So it's a little bit, so it shrunk. Now, what happens if I increase my sample to maybe 20 or 25? So what will happen was that I'll go ahead and animate it. So in this case, I'm going to increase my sample size. I'm not gonna take 5. Now I'm gonna take 25 of them. Get them all, add them together, divide by 25, and what I'm gonna get is a new observation. Okay, and that's gonna be the mean of those 25 that I just got. If I keep doing this over and over and over again, notice that I still get a normal curve. The means are about the same. The standard deviations now are different. Here, the standard deviation is 5, and the standard deviation here is 1. Okay? So, what does this mean? Well, that means that if I continuously increase my sample, right, if I get a whole bunch of samples, and I get those particular samples, add them together and divide it by the total, and I start plotting all those individual means, I will get a normal curve. Okay, now this kind of makes sense because you started off with a normal curve. Now, what about if I didn't start with a normal curve? Well, what about if I started off with a skewed distribution? Well, if n was equal to 5, and I did this again, and I did this many, many different times, you will get something that kind of looks like a normal curve. Not quite. It looks a little bit skewed. But what would happen if I increase n equals 5? So maybe n equals 5 didn't quite make it, okay? But what about if I increase it to 25 and I do this over and over and over again? Well, what I'll get is actually a normal curve, which is actually pretty amazing because it doesn't really matter what my original looks like. So I can make any original population maybe something like that looks like that. And I get maybe just 5, do it. You still somewhat get of a normal distribution. If n is greater, like 25, and I keep doing this over and over and over again, I start to approach something that looks very normal, which is really, really fascinating. Okay, so what does this mean? So what this means is, not that. Leave doesn't matter. Okay, so these notes are on Blackboard. So this means this is actually the central limit theorem for means. So it says the sampling distribution of the sample mean approaches a normal distribution as the sample size gets larger. So in other words, x bar is normally distributed with a mean of mu and a standard error of sigma over square root of n. So here this thing is going to be my mean. This thing is going to be my standard deviation or my standard error. Oh, that's wrong. Standard error. Okay, so here we have something very similar to what we had for the proportions. For proportions, we had that p hat was normally distributed with a mean of p and a standard error of square root of p, 1 minus p divided by n. That's what we had for sample proportion. Now for the sample mean, we have a completely different distribution. Okay, now in order for me to use CLT for means, you require the sample size n to be large enough. Okay, so in this class, large enough is going to be n has to be greater than 25. This is very different than p hat because p hat we had n times p greater than or equal to 10 and n times 1 minus p greater than or equal to 10. In this case, we just require that n is greater than 25, greater than or equal to 25. So make sure that you really understand these scenarios because there might be something like a true and false question there for the next upcoming exam. So if the original population is normally distributed, then the sample size does not matter. You can use the central limit theorem for means. And that makes sense because when this thing was originally normal, it didn't really matter whether n was 2 or 5 or whatever, I still got a normal curve, okay? Now, so that one, basically n doesn't matter. N can be whatever you want. If the original population is not normal, so if I had skewed, then, but n is greater than or equal to 25, then I can use the central limit theorem for means. So I require that so if it's not normal, but n is pretty large, n is greater than or equal to 25, then I'm in the clear. I can go ahead and use that. If the population is not normal and n is less than 25, then I cannot use the central limit theorem for means. So I have to do something completely different. Okay, so those are the 3 different scenarios that you'll kind of encounter. So in the next video, I will go ahead and do this upcoming example.